In this video, we're going to address the derivatives of the inverse trig function. And like the last section, this is going to be pretty heavy stuff, so let's get right into it. I'll probably not be able to do this all in one video. I'll probably have to break this up into pieces, but let's see how it goes. I'm going to start with the graph of y equals cosine of x. Everybody is familiar with this thing. Its range goes from -1 to 1. It's defined for all real numbers. It's continuous everywhere. It's differentiable everywhere. It's the one that some people say starts up high, whereas sine starts at 0, 0, etc. Well, one thing that it is not 1 to 1. It is not 1 to 1. What that means is that the cosine function does not have an inverse. So y equals cosine of x has no inverse. So how can we even talk about inverse trig functions then? Well, what we do is we cut it down to size. We pick a length of it that will somehow tell us everything there is to know about cosine of x, but be 1 to 1. So what we've done here, down here, this thing here is cosine, but it's only from x equals 0 to x equals pi. It's just that piece of cosine. There's some reasons why that's chosen as the place. One, in this restricted domain, the function is 1 to 1, so it does have an inverse. Plus, you happen to know that this behavior, when it is on cosine, not only happens here, but it also happens here. It's the exact same thing, it's just shifted by 2 pi units. And the same thing would happen here. Not only that, if I were to turn this around, reflect it about the line x equals pi over 2, what I would get are these pieces of graph. So the point of this is that with only this piece of graph, I can solve any problem. I just need to know where the angle is occurring. Like, for example, if I'm anywhere between 0 and pi, this one piece already has it taken care of. But if I'm somewhere between, let's see, 11 pi and 12 pi, for example, I would want this kind of a piece, and then I would shift it over appropriately. So with this in mind, I've specifically called this y equals cosine of x because I want to use the notation f of x equals cosine of x for what we have. All it is cosine, but limited to 0 to pi. So let's put its domain is 0 to pi. Its range is -1 to 1. And then I'll make use, I'm gonna put some points on here so that that's 0, 1. I think, what is this one here? That's pi over 2, 0. And you can see them on here, but I'm putting them here because I'm going to make specific use of these in a minute. And then we have pi, comma, -1. All right, so I can define an inverse on just this particular function. We will call the inverse f inverse of x will be called cosine to the negative 1 x. This is a horrible notation. Everybody is aware how horrible it is, but nobody has thought to change it. So please do not confuse this with 1 over f or 1 over cosine. That is not what that notation means. It is a horrible notation to represent an inverse function. So without actually looking at the graph, I can tell you some things about it. For instance, since x and y change positions as the inverse, that means the range and domain swap also. So I can tell you that the domain of this one, the inverse function, will be the range of the original function. So the domain will be negative 1 to 1. And then the range of the inverse will be the domain of the original. Remember, you're switching x and y in every conceivable fashion. Now, I'm just going to scribble out something, but then I'll have the computer draw a nice graph. Oops. All right, so I know the domain will be from negative 1 to 1. I know the range will be from 0 to pi. So, I don't know, let's make this a little bit higher, I suppose. Put pi up there. Now this is where I'm going to use the points. On the original function we had 0, 1, so the point 1, 0 is on the inverse. So I'll put a dot at 1, 0. 1, 0. On the original function we have pi over 2, 0. So on this function down here, I will have 0, pi over 2. So let me put a pi over 2 in here. We'll have a point here at 0, pi over 2. And then finally, I had a point at pi negative 1 on the original. So I will have a point of negative 1 pi on this graph. So negative 1, let me go up to pi. And now I need to connect these 3 points similar to how I have this, because the graph is going to have the same shape, it's just reflected. Now if you look right around here, right around at 0, 1, the graph kind of looks like it's becoming horizontal. In fact, it is. It's becoming horizontal right there. That means at the same point, but the reversed point, the graph will be becoming vertical. So I'll have something that starts like this, start almost vertical, and then I'll go through, it kind of slides through pi over 2, 0, until it goes horizontal again at pi negative 1. So I know at pi negative 1, it's going to be somewhat vertical, come down, and then do something like that. Do you see it? Horizontal, vertical, horizontal, vertical. What that means is at this place, you have a horizontal asymptote, but you'll also have the slope of the tangent line will be 0. Here, the slope of the tangent line will be infinite. So, without further ado, let me actually grab a picture of it so that we can take a look at a really good picture of it. All right, here we have it, just as I mentioned. Right there, we have negative 1, pi. This is f inverse of x equals cosine inverse of x. I don't say cosine to the negative 1, I say cos inverse. That way I don't confuse myself. And you can see all the things are the same as I wrote up there. 1, 0. And there was 0, pi over 2. Notice it's differentiable. You should understand that it's considered differentiable not from negative 1 to 1, including negative 1 to 1, but it'd be differentiable from negative 1 to 1 without including the endpoints. So it'd be differentiable. So what I'm saying is the derivative is not going to exist at either 1 or negative 1. In fact, it's not going to, it just won't be finite. But anyways, the domain and range are like I said before. We have, these are the points that we got to keep in mind. Now, you're familiar with this. If I have f of f inverse of x, that equals x. Now that's going to depend on domains and things like that. But with that in mind, my f, let's say, was cosine. And then I'm going to have cos inverse of x. And that should equal x. Not for all x's in the world. We have to pass through this first, which means since cos inverse is only defined from negative 1 to 1, this is for x values that are between negative 1 and 1. Next, we have f inverse of f of x equals x, and same stipulation as before. We could have some issues. So we have cos inverse of cosine of x equals x. But now, where is cosine defined? Well, in order to have this inverse discussion, cosine, remember, is defined only from 0 to pi. So this is good for x between 0 and pi. So let's develop a derivative. All I'm going to do is develop derivatives, talk about some theory, domains and ranges, all that kind of stuff, and then we'll do examples in the next video. So let's start with this equation here. I'm going to take the derivative of both sides of that. So I'm going to take the derivative d over dx of cosine inverse of x equals d over dx of x. Now, what you have here is the outer function is cosine, the inner function is cos inverse, so you got to use the chain rule. The outer function's derivative is negative sine. So I end up with negative sine of cos inverse of x. Then you've got to take the derivative of the inside, which we have been calling cos inverse prime of x. What I'm going to try to do is get the formula for cos inverse prime. The derivative of x with respect to x is just 1. Now, I come across some complications that I should probably share with you here. Sine and cos inverse of x. I want to get a combination, some sort of a connection between these two. And for most of you, you're used to doing something like this. Seeing cosine and sine having a relationship such as that. Now, I don't want to label anything just yet, but let me put a theta down here. What I'm going to do is I'm going to allow theta to equal cosine inverse of x. This should make sense. You use cos inverse to tell you what the angle was before you did anything. So it makes sense to call it theta. Well, anyways, cosine of theta then equals x. On this 0 to 90 degrees or 0 to pi over 2, everything goes here. So cosine of theta equals x. Well, you know that cosine of theta equals, let me see, adjacent over hypotenuse. Well, one way to make that happen is if I thought of x instead as x over 1, I could label this triangle as x as the adjacent side and then 1 as the hypotenuse. And then use the Pythagorean theorem to get the other side as 1 minus x squared. Okay, now, if you're trying to figure out what sine of cos inverse of x is, sine of cosine inverse of x equals sine, instead of cosine inverse, I'm going to put the theta, sine of theta. Now reference this triangle. Sine of theta is opposite over hypotenuse. then let me copy this equation. Then I can replace this portion of it with the square root of 1 minus x squared. Don't forget I'll bring down the minus sign. Then I have cosine inverse prime of x equals 1. So now I can solve for cos inverse prime and get cos inverse prime of x equals negative 1 over the square root of 1 minus x squared. Now some caution. Whenever you do a triangle like this, you're under the patent assumption that theta has to be between 0 and pi over 2. Well, unfortunately, cosine inverse, when it's giving back the thetas, what does cosine inverse give us? Cosine inverse gives us angles that are between 0 and pi. Well, we luck out in this particular case because for angles between 0 and pi, that are angles in the first and second quadrant, sine itself is positive over that entire quadrant. So I don't have to worry about any kind of plus or minus business happening. This is the formula for all possible x's that we permitted to use. So the derivative of cosine inverse of x equals negative 1 over the square root of 1 minus x squared. I don't think I need to specify the values of x. I think you can see that we can't allow x to be negative or positive 1, so x has to be between negative 1 and 1, but not including negative 1 and 1. Now the reason I chose cosine is because most textbooks usually deal quite a bit with sine. They'll develop the formula for it and then say, oh, okay, now you go and do cosine. Well, I decided to do the opposite. I've done cosine. I'm going to leave sine to you. But there is one thing I want to show you. There's a formula that goes like this. Cosine inverse of x plus sine inverse of x always equals pi over 2. This is because the CO in cosine means complementary sign. When two angles are complementary, they add up to pi over 2, or 90 degrees, whichever way you want to think about it. Since cosine gives an angle and sine gives an angle, think of it this way. I get an angle by taking the inverse sine of something. Then the complement of that angle is covered by this piece. So together they equal pi over 2. Well, that's great because then I can take the derivative Well, the derivative of pi over 2 is easy. It's just a number, so it's 0. The derivative of cos inverse x, well, remember I can break this up, assuming that both derivatives exist. Now, before even knowing it, I'm going to subtract d over dx of cos inverse x. This is important. All of the original trig functions and their co-functions all behave like this. Anyways, I already know what that one is. That was negative 1 over the square root of 1 minus x squared. And so d over dx of inverse sine equals 1 over the square root of 1 minus x squared. Now, what I encourage you to do is this. Your book is going to inevitably do inverse sine as its first example on developing a derivative. So if I were you, they're going to do all the stuff that I said, almost word for word probably. So go follow that and see if you can keep up with while you're doing sine. Moving on. The next major function is tangent or cotangent, whatever way you want to look at it. And I think what I'll do is develop, I'll stick to the book with this one, and you can then try to develop cotangent on your own. I'll write a few things about it. Give me a minute. So let's start with y equals tangent of x. As you can see that, like the other functions, it is not one-to-one at all, so it doesn't have an inverse. However, if I restrict it to a certain domain, the reasoning seems to be this: stick to the closest to the origin you can, but have a section that is one-to-one. So let's keep that in mind. So I'm going to pick between negative pi over 2 and pi over 2. I didn't pick it, but that's the one that is always picked. But you get the idea. Negative pi over 2 to pi over 2 will be the function we're considering. So let's list this. The function f of x equals tangent of x. Now these are for the purposes of getting an inverse function. I'm going to define the domain will be negative pi over 2, not including negative pi over 2, to pi over 2, and of course not including that either. The range is negative infinity to infinity. And I'm not exactly sure where to get some points. The 0, 0 isn't going to make much of a difference when I take its inverse, but the domain and range will have some validity. Let's see how much I can do. Now keep in mind too, these are vertical asymptotes, so let me do that. We have vertical asymptotes. VA are at x equals plus and minus pi over 2. That means we'll have horizontal asymptotes for the inverse. So the inverse then, all right, now I have a graph of the inverse function, f inverse of x equals tan to the negative 1 of x. And you can see that my range is negative pi over 2 to pi over 2, just like the domain of the original function. So let's write that down. Domain, let's write the range, but the domain is negative infinity to infinity, which matches the range of the original. And the range, as I said, was negative pi over 2 to pi over 2. The horizontal asymptotes are, as I said, HA. This time they are y equals plus and minus pi over 2. Here's another thing. Students tend to forget this a lot of times, the limits. I didn't write them up here because you only had the limit as x went to pi over 2 from the left or x went to pi over 2 from the right. But over here, look at this. As x goes to infinity, this function is going to pi over 2. That's a horizontal asymptote. So let me write those down. Limit. Keep this in mind. I'm telling you, you'll forget it if you don't write it down. So you have that going on there. And as before, we have tangent of tan inverse of x equals x for all x in R. For all real numbers x, because the domain of tan inverse is negative infinity to infinity. Now if I flip it, if I do tan inverse of tangent of x, that'll also equal x, but it will be only for negative pi over 2 less than x less than pi over 2. So I'll do the same sort of a game that I did before. I'll start with this one here, and I'll take its derivative. So d over dx of tan inverse of x equals d over dx of x. Of course, that side is 1. The derivative of the tangent function, the outer function, is secant squared. So I'll have secant squared of tan inverse of x, and I foolishly did not leave myself enough room over here, times tan inverse prime of x. That's equal to 1. So I'm going to play the same game I did before. I am going to let theta equal tan inverse of x. So if theta equals tan inverse of x, then tangent of theta equals x. So you're probably going to want to think of that as x over 1 again. Make the triangle, but be wary of the limitations of the triangle, because it's only going from 0 to pi over 2. I'll put my theta in here. Tangent theta is adjacent, no, opposite over adjacent, so I'll put an x here and a 1 here, and then the Pythagorean theorem tells me this is the square root of 1 plus x squared. So what I need to figure out is secant squared of theta. So secant squared of tan inverse of x is the same as secant squared of theta. Well, secant of theta is hypotenuse over adjacent. So it's the square root of 1 plus x squared over 1. But then I got to do secant squared, so I got to square this. So that equals 1 plus x squared. So let me grab this guy up here. This was the thing I was working with before. Let's see how much I'm able to grab. Bring it down here. And what I just did, this part right here, was 1 plus x squared. So if I divide both sides by 1 plus x squared, I'll get the formula d over dx tan inverse of x equals 1 over 1 plus x squared. Notice this is good for all x's, for all real numbers x. Now, I should be careful here because I did not, like I said, this angle here only goes between 0 and pi over 2, but tan inverse goes from negative pi over 2 to pi over 2. So what's the deal? Isn't this positive some places and negative some others? Well, let's take a look at what did we have. This is the place where we had to deal. Well, it's not going to matter whatever tan inverse is positive or negative. What's that going to do? When you square it, you're automatically going to be positive. So I don't have to worry about a plus and minus situation occurring to ruin things for me. Now, I thought you might find this interesting. All right, I've taken the liberty to graph tan inverse of x plus cotan inverse of x. Let me show you the graph of it. I've got it hanging over here. That it is pi over 2 like it's supposed to be, but when x is greater than 0, and it's negative pi over 2 when x is less than 0. This is going to equal pi over 2 when x is greater than 0, negative pi over 2 when x is less than 0. What is it actually at 0? Let's come back to the program. It actually allows me to calculate values. So I'm going to go and evaluate, and let's see what happens when x equals 0. Division by 0, error 7. And it introduces a discontinuity. I can take the derivative of that thing. I'll get d over dx of tangent inverse of x plus d over dx cotangent inverse of x equals d over dx. This may look weird, but I'll explain it in a minute. Pi over 2 when x is greater than 0, negative pi over 2 when x is less than 0. So, we've gone through the effort of doing the derivative of tan inverse. We put it in. 1 over 1 plus x squared. Now over here, I'm going to get, well, nothing yet. I'm calculating that dx. Cot inverse of x. And this equals, now over here, we're going to get a 0 if x is greater than or equal to 0, or greater than 0, and also 0 when x is less than 0. The derivative of constant is 0. So that's 0 for everything except x equal to 0. But that's only because of this stuff. There's a discontinuity between the, ignoring the 0 that is the discontinuity from their sum. I have 1 over 1 plus x squared plus d over dx cot inverse of x. And then when I subtract 1 over 1 plus x squared, I end up with this. As you should now getting the idea of the derivative of the arc cofunctions is the negative of the derivative of the arc initial function. And that leaves us with perhaps the most nastiest of all the trig functions, and those are the things like cosecant and secant. It's because of the way they're shaped like this. Look at this. They have so many discontinuities. But you remember, if I were to draw sine, the graph of sine in here, it would come in here and just touch at each of these places. But I don't think there's any need to do that. Now, like any of the other trig functions, it does not have an inverse function because it's not one-to-one. Going down here, we break it up into pieces, and this is the function I'm going to work with. So I'm going to define f of x equal to cosecant of x as being the function displayed here. It's basically I take cosecant and I limit the domain from negative pi over 2 to 0, union 0 to pi over 2. So let's write this stuff down. My domain is negative pi over 2, it's including that, to 0, but it's not including 0, union 0 to positive pi over 2. And the range, let's see the y values that are taken up here. We go from negative infinity to negative 1, including negative 1. So we have negative infinity to negative 1, bracket, union, 1 to infinity. And that's this part. The y values that it takes up go from 1 to infinity. I also have this vertical asymptote of x equals 0. Okay, and then for my reference, I want to graph this thing, so I'll put a dot here, and that'll be pi over 2 comma 1, and over here is negative pi over 2 comma negative 1. Now make note, look at the way the graph hugs the vertical asymptote on either side of it. Well, our inverse is going to hug the horizontal asymptote in a similar way. For instance, the horizontal asymptote, as y goes up to infinity, the graph is getting closer and closer from the right of it. So when we take the inverse, I'll have the graph will be hugging the x-axis as x goes to positive infinity. Let's see if I've already graphed it, and I have. As you can see, this is exactly what I was talking about. Right here is 1 comma pi over 2, Remember, switch the x and y values. So you switch that one, becomes this, and this piece here corresponds to this piece over here. And then on this piece, the inverse of that piece is over here. So let me go ahead and make a dot, and then we have -1, comma, negative pi over 2. That -1 looks terrible, so I can take it out without erasing a bunch of other stuff. Alright, so our domain is -infinity to -1, union 1 to infinity. Let me check. That matches the range of the original function. And then the range would be, with the y values you take up, from -pi/2 to 0. It doesn't actually have 0 because it doesn't touch the x-axis, but then from 0 to pi/2. So -pi/2 to 0, union 0 to pi/2. Got it. Alright, and horizontal asymptote is y equals 0. I'm going to make use of this particular identity. And there's the f inverse, but that doesn't help me in taking the derivative. So let me go ahead and put the corresponding functions in their place. I have cosecant of cosecant inverse of x equals x. And what values of x is that good for? Well, whatever the domain of cosecant inverse is. And the domain is -infinity to -1. So this is for x in -infinity to -1, union 1 to infinity. Let's take the derivative of both sides. The hope is by the time I do this the third time, you'll be like, oh, this is so rote that it won't seem a problem when you go to try to do it yourself. So if I take d over dx of both sides, here's what I get. Now the basic derivative for the cosecant function is negative cosecant times cotangent. So let me go ahead and put that in. So I'll have negative cosecant of cosecant inverse of x times cotangent of cosecant inverse of x times the derivative of cosecant of s inverse of x. So I have CSC inverse prime of x, and as usual this equals 1. Now this piece is really simple here. Cosecant and cosecant inverse is just x. So I can simplify this a little bit by dividing by negative x. Okay, and as I always do, I'm going to try to figure out some sort of an algebraic expression for this piece here. So like we did in all the other problems, I will let theta equal cosecant inverse of x. Now you need to be a little careful here. Let me back up just a second. Cosec inverse is negative when x is less than or equal to -1, but it's positive when x is greater than or equal to 0. Or another way to look at it, cosec inverse gives angles. So when it outputs an angle here, you have two situations. Either it's outputting a negative angle between -pi/2 and 0, or it's outputting a positive angle between 0 and pi/2. So what I'm going to do is I'm going to break this into cases. Case 1. I'll look at the case where theta is greater than 0, but less than or equal to pi/2. So if you remember, this means that theta is in the first quadrant. Everything is positive there. And then this triangle, the one that I keep telling you you have to be worried about its limits, I don't have to worry about it here because I am operating from 0 to 90. So this triangle is perfectly fine. The only thing we'll have it at 90 or pi over 2, we have straight up and down. Those are going to be the limits of what we're doing. So if theta equals cosecant of x, then if I take cosecant of theta equals x, and cosecant, remember sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite. So I'm going to put an x here and then a 1 here. That's hypotenuse over opposite. The Pythagorean theorem fills out the rest. My equation that I had up here, let me copy it. Cotangent of theta. Tangent is opposite over adjacent, so cotangent is adjacent over opposite. So this piece right here is the square root of x squared minus 1. So I can divide by that, and I get cosecant inverse prime of x equals -1 all over the square root of x squared minus 1. So you can see it's having some issues there at plus or minus 1, as we kind of suspected it would. Now, there was a second case. Theta still is equal to cosecant inverse of x. But the second case is where theta is between negative pi over 2 and 0. So that places it in the fourth quadrant. Now things are a little bit different here. Let me go back to the equation that I had. I still have this equation there because the -1 over x doesn't change anything. If the theta is in the fourth quadrant, or you can even look at it this way, I have a picture like this. Now I'll draw my reference triangle down here. Theta would be in here. Okay, can I make that theta-ish? Good, theta is there. Now, we still have cosecant theta equals x. Cosecant is still hypotenuse over opposite. So I'll have x and a 1 here. Now here's where the issue is. X is most definitely negative in this case. The problem with it is I have it on this picture. And unfortunately, for cosecant of x to be in here, let's go back to the graph quickly. If my cosecant, if the range is in here, that means the x values had to have been negative. So, if the x values have to absolutely be negative, then I should probably put a negative in front of that so that it's a positive number. Hypotenuse can't be negative. Same thing happens though, x squared minus 1 here. Now when I do cotangent, now keep in mind that cotangent of theta is also negative in this quadrant. It equals adjacent over opposite. However, it should be negative because cotangent is negative in that quadrant. This piece right here now is a negative square root of x squared minus 1. Now I'll divide both sides by that, and I get cosecant inverse prime of x equals positive 1 over x times x squared minus 1. So, here's what I have. Let me write down my results. I have d over dx cosecant inverse of x equals -1 over x square root x squared minus 1. This is when x is greater than or equal to 1. And d over dx cosecant inverse of x equals positive 1 over x times the square root of x squared minus 1, this time when x is less than or equal to negative 1. So if you look, if x is less than or equal to 1, this is a negative number. And if x is positive, this is also a negative number. Well, a nice little thing I can do is combine this into just one formula by invoking the absolute value formula. D over dx cosecant of x, cosec inverse of x, equals negative 1 over the absolute value of x times the square root of x squared minus 1. Check to make sure that makes sense. No matter what x is now, this is going to be a negative number just because of that absolute value. So the entire denominator is non-negative. Well, it's got to be positive because it can't be 0. So this makes it so we always have a negative number. If x is positive, this is negative. If x is negative, this is negative. So it all agrees. Now, let's take a look at cosecant inverse with its, I guess, origin function, secant inverse of x. And let's graph those two together. And you can see that for the applicable x values, less than negative 1, less than or equal to negative 1, or greater than or equal to 1, we have pi over 2. So as before, I can take the derivative of the whole thing. Now let me go ahead and put in what I found for the derivative of cosec inverse. That was negative 1 over the absolute value of x times x squared minus 1 plus d over dx sec inverse of x equals 0. Add the 1 over absolute value of x times the square root of x squared minus 1 to both sides, and we get the formula for the derivative of inverse secant. So there you go. All 6 of the trig functions have their derivatives.